Section 1.3, differentials. The differential is something defined very similarly to the derivative in this sense. Suppose a function f is differentiable at a point x in its domain. Now for the differential, we will consider x fixed. In other words, we'll consider one x at a time. Now the dx is the independent variable, and it can be any size whatsoever. It doesn't have to be small. dy is the dependent variable. And of course, what I'm saying is that dx is one variable. It is not two variables. Okay, no, this is the only time in math that I can think of right now that you use two letters to represent one variable. So, but dx is one variable and it doesn't need to be small. And dy similarly is just one variable. The relationship of dx and dy are defined as such. That is, dy is f prime of x times dx. Again, dx might not be small. This is just a linear relationship. What it does is at the point of x, let's say this is the function f, and this is x, okay? This is x. The dy equals f prime x dx. This describes the straight line, the tangent at that point. The tangent that's moved over because this doesn't have any constants in it. So it's not exactly in the right place, but this describes that tangent, okay? If you were to move this tangent to the origin, that would be its equation. And that is the complete description of the differential. The differential described such turns out to have very convenient properties. For example, the composite rule of differentiation works. In fact, all the rules of differentiation works. For example, let's say if you have a function y equal to f of x, and let's say everything is differentiable. We don't worry about that. And then let's say x is a function of something else, g of t, okay? Now, if we do so that together y equals to something else, if you plug it in, f of t, which is the same as f of g of t, okay? We'll together call it big F of t. So then, if this is true, if you calculate this, you can use the same rules and everything will come out as we can see like this. So by definition then, dy equals to f prime of t dt, okay? But it also equal to dy originally equal to f prime of x dx. Now, do these two values coincide? Are they going to be the same? Well, if you do it through the composite rule of differentiation, they will come out like this. So if you look at f prime of t is what? Now, f prime of derivative with respect to t, you do the composite rule for this, is f prime of x times g prime of t. All right? And then therefore, so then if you do dy is do it the hard way, so then okay, we'll just do dy then equal to plug this thing in here, which is this, which is f prime of x g prime of t dt. And that part, what is this? This is the same as f prime of x. G prime t dt is the same as dx, because dx, as we can write it here, from here, dx is be equal to g prime of t dt. So this substitute to be the same. So as you can see, the dy expressed this way is the original way. So when you use a third variable, everything still comes out the same. In general, the differentials work exactly the same as derivatives in all the rules. That is, say, if you have a y equals to u times v, then dy will be like u dv plus v du. That is the product rule, and of course the quotient rule works the same way. And in the next video, we are going to do an example of the differential. The reason we do differential, one reason is because it's somewhat easier to work with in a lot of times, especially if you have a third variable, than to work with derivatives. But they work out nicely the same way. So